Problem number 22, evaluate this limit. This is what I sometimes call almost like a joke problem because it's not serious in the sense of other problems. Our natural reaction is to start thinking about paths and, two-path tests or polar coordinates, depending on what we're trying to do here. But realize that when we plug in 1, 1 in for here, everything's fine. We can just plug this in. The function we're taking a limit of is a continuous function. And so we can simply evaluate this limit by substitution. So we plug in x is 1, y is 1. We end up with sine of 2 plus 1 upstairs and 3 downstairs. And this is our final answer, and that's all the work we have to do. Nothing more. This is it. Okay, so that's problem number 22. Problem number 23 is going to be a little bit more work. We want to show that this limit here does not exist. How are we going to do that? Let's use two-path test. Let's think about paths of the form y is equal to mx for constants m. Okay, when we make the substitution, so this limit x goes to 0 now. 5x squared minus 2 times mx squared. Everywhere we see a y, we replace it with mx. Okay, so we end up with limit as x goes to 0 of 5x squared minus 2m squared x squared over 7x squared plus 3m squared x squared. And we see that there's a factor of x squared in every term, both upstairs and downstairs. So we can get rid of those terms. And what are we left with? The limit as x goes to 0 of 5 minus 2m squared upstairs over 7 plus 3m squared downstairs. This does not depend on x, so the limit here is 5 minus 2m squared over 7 plus 3m squared. So this is what the limit is as a function of m. All we have to do then is just to see that if we plug in, say, m is equal to 1 in here, the limit is 5 minus 2 over 7 plus 3 is 3/10. And let's just pick a different m value, like m is equal to 2. We would get, looks like negative 3 over 7 plus 12 is 19. These are not equal to each other. These are not equal to each other, so the limit does not exist. Okay, so that is what is going on in problem 23. Let's go for one more problem in this video. Problem 24. We want to show that this limit actually does exist, and then show that this limit actually does equal to 0. So my preferred method for showing that a limit like this equals 0 is by using polar coordinates and the squeeze theorem. So we're going to replace x is equal to with r cosine theta, y is equal to r sine theta. And so when we make these replacements, the function we're taking the limit of is going to become 5 times x squared is going to be r squared cosine squared theta minus 2 times r squared sine squared theta, all of that over the square root of x squared plus y squared. We should recognize that that's going to be r. Okay, let's see, what can we do here? So I'm going to put absolute value bars on the whole thing. So we know that this is going to be non-negative. And this is going to be, let's see here, r isn't going to be negative, so we can move that outside here. There's a factor of r squared upstairs that I can move outside, so that all this times absolute value of 5 cosine squared theta minus 2 sine squared theta, like this. Those factors of r cancel out. So, oops, I don't know why I got rid of that. Less than or equal, that should be back here. And this is going to be, I guess it's a strict equals, not a less than or equal. It's just equals, but doesn't matter. R times 5 cosine squared theta minus 2 sine squared theta. And now I'm going to use triangle inequality. The absolute value of this minus this is less than or equal to the absolute value of this, the first term, plus the absolute value of the second term. So that is a known inequality there, triangle inequality. Now, cosine squared theta is always between 0 and 1. So the biggest this term can be is 5. Sine squared theta is also always between 0 and 1, so the biggest this term can be is 2. So this is less than or equal to r times 5 plus 2 is 7r. So let's take a moment just to step back and see what we've accomplished here. That the function that we're trying to take a limit of, we slap absolute value bars in the whole thing and convert to polar coordinates. This is never less than 0, so it's greater than or equal to 0, but it's also less than or equal to 7r. And so here's where squeeze theorem, sandwich theorem, whatever you want to call it, comes into play. The limit as r goes to 0 of 0 is equal to 0. The limit as r goes to 0 of 7r is also equal to 0. So the limit as r goes to 0 of absolute value of 5r squared cosine squared theta minus 2r squared sine squared theta, all that over r, this must also equal 0. The limit of this is 0, the limit of this is 0, so by the squeeze theorem, sandwich theorem, the limit of this term must also be 0. But this is just, this is just the limit as x, y goes to 0, 0, converting back to x, y, absolute value of 5x squared minus 2y squared over square root of x squared plus y squared. This limit must equal 0. And the final thing here is that the limit of this with absolute value bars on it equals 0, if and only if the limit of it without absolute value bars on it equals 0. And so that shows how we can use squeeze theorem, sandwich theorem, and polar coordinates to show that this limit here does exist. This is my preferred way of showing that this type of limit does exist.